Okay. Now what we have here is the same question, right? The same question which we earlier solved using impulse momentum theorem and equations of motion. Now we'll try to solve the same question using work energy theorem. Can you state the work energy theorem and explain the various keywords in it, like the relevance of the phrase F external is equal to 0 in conservation of momentum theorem? Do you have any such words in work energy theorem? Okay. Now, while we use work energy theorem, we are always under the assumption that we ignore drag offered by the air, column of air, and other influences which disturbs the line of path of the ball heading towards the cricketer. So we assume that the only force acting along with the weight is the force coming from the hand. Okay. So if we consider the forces acting on the ball, there are only two. One, weight acting perpendicularly downwards, and the horizontal force from the hand. Now, when I say this, I also assume that the ball is coming horizontally and the player is catching it horizontally as well, but in the opposite direction. Okay. So we'll call this as F, and this U represents the initial direction of motion of ball. Now, there are two things that are very important here. One is that since the initial direction of motion is along the positive x-axis, so will be the direction of displacement. Why is direction of displacement important here? If you answer this question well, it means that you did go through what we have discussed in work energy theorem. Now, if you're here for the first time, let's go through things in detail. So, weight is acting downwards, so vector acting downwards. Displacement is a vector acting horizontally towards the right. Therefore, theta, the angle between them, is equal to 90 degree. Similarly, we have vector F acting towards left horizontally. Displacement is acting towards the right horizontally. Therefore, the angle between them is 180 degrees. Why is this important? Because by work energy theorem, work done by all the forces on the ball is equal to change in kinetic energy of the ball. Change in kinetic energy of the ball is in turn equal to kinetic energy final minus kinetic energy initial, which is half mv square minus half mu square. What is work done by mg? Work done by any force is force dot displacement, right? Work done by any force is force dot displacement, the dot product of that force and the displacement. What is the force here? Weight vector mg dot displacement vector s. Similarly, work done by the F external here is vector F dot vector S. Now, what is vector F dot S? Oh, come on. We have done a lot of problems based on this, right? Basic dot product. Maybe just write it down here. So vector A dot vector B is equal to magnitude of vector A times magnitude of vector B times cosine of the angle between these two vectors. So magnitude of mg is mg, magnitude of displacement is s times cos of angle between mg and s. That's where this analysis become important. What is angle between mg and s? It is 90 degrees, right? So that is cos 90 here. Magnitude of vector f, magnitude of vector f is f, displacement is s, cos angle between f and s, which takes us back to the diagram. Angle between vector f and s is again 180 degrees, which makes this f into s into 180. is equal to 0 squared. Why 0 squared? Because the ball is finally at rest. U is given to us as 20 meter per second, so 20 squared. Now, cos 90 is 0, therefore this term vanishes, right? Cos 90 is 0. Now the only term is f into s. Cos 180 is minus 1. My bad. Cos 180 is minus 1 here, equal to minus half into 0.150 into 20 square. Now, we have to find out the magnitude of force, which is F hand. And the RHS is clear with numbers, but we don't know S here. Now, displacement is unknown, which can be figured out by U plus V by 2 into T, the average velocity into time, which is initial plus final velocity by 2 into time, which is zero point 0.1. And therefore, displacement is 20 by 2 times 1. If I plug in this value to the previous equation, what we get is F hand into S is equal to minus half into 0.15020 square. And what we do is we plug in this value of S into the equation here, 20 by 2 into 0.1, right? So 20 by 2, 20 by 20 is 1, 2 by 2 is 1. Oh, there's one minus here, right? Minus, minus, and minus. So 0.150 into 20, which gives us 30. There is already a minus here, which will turn this negative into positive, which gives us F is equal to 30 newtons. Okay. So this is the most important transition here, something that we should be able to understand well. Now, what did we achieve here so far? Discussing only one question. Yes, but we did solve it using equations of motion. Then we saw the difference between applying conservation of momentum theorem and impulse momentum theorem. And now we solve the same question using work energy theorem. Okay. Now, this is what I suggest. This is what I very personal recommend that you should be trying to do with every possible question that you can find in the previous questions, looking at multiple ways to solve the same question. Of course, it doesn't work for every chapter. It works only in certain set of chapters for that matter. But those set of chapters will have many interlinked, intertwined concepts, and you should be trying your best to explore it. That's what we're trying to do here, right? Okay, now moving to the next question.